Hello everyone, welcome to Technologies Discussion channel. Today, I'd like to continue the discussion on EMC consideration. Okay, so for this video, I'm going to discuss the testing procedure of conductor immunity using this CDN method. CDN actually stands for coupling decoupling network. I also will emphasize what is actually inside the CDN. Okay, so basically, this is the objective of this video. This will be the part 68 series discussion on EMC. So guys, if you're keen to know more about EMC, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on EMC. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, okay, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Okay, so basically what we have discussed on the previous discussion, part 67 series discussion, I have discussed how can we actually perform conductor immunity using CDN and also EM Okay, someone sent me an email. Okay, you are right. Thank you so much. There is another method to do conductor immunity, which is the BCI. BCI stands for bulk current injection clamp. Okay, so but this method is so-called already is so-called face up. So therefore, this is why I never discuss. But as I agree, okay, so I need to give you some update, okay, why this method of doing conductor immunity so-called already face up. Okay, wow, there are some standard that actually specify that conductor immunity testing to be carried out with BCI clamp. Okay, but this IEC EN 61000-4-6, they actually specify that when you actually do conductor immunity, you can use any of the above listed method. So basically, you have these three method. Okay, so based on this so-called standard, you are actually allowed to do any one of them. Okay, but okay, this standard actually also indicate that it actually give a clear priority to CDN. Okay, which means that if possible, okay, you are going to encourage to do this conductor immunity using CDN rather than the other two method. So if you can use CDN, if you cannot, then actually they also allow you to fall back on another these two method. Okay, the prefer for CDN comes from their property to establish a well-defined RF impedance of 150 ohm. Okay, so this video, okay, I will also so-called discuss a little bit on this RF impedance of 150 ohm for the CDN. Okay, because CDN can give you a very well-defined of impedance. So therefore, once you have this so-called well-defined impedance, then your result will be consistent. So hence, because of this, CDN is always the preferred method. Okay, as it mentioned here. Okay, another reason, okay, because CDN also have this biggest advantage as compared to this BCI clamp is because they can actually offer coupling and decoupling in a single device. You probably very confused what is called coupling and decoupling. Okay, so this video I'm going to explain what is also coupling and what is also decoupling. Or maybe I should say that I will discuss the difference between coupling and decoupling. EM clamp, okay, so basically will be the next prefer. So if you cannot use CDN, then you need to use EM clamp. Okay, so they are only used when it is not possible to use a CDN. Okay, both method, which means that the CDM and EM clamp, they actually offer both coupling and decoupling. Okay, but BCI cannot, which I'm going to explain later on. Okay, so let me quickly introduce this another method to do conductor immunity, although so-called already face up, but I'd like to give you some idea how this can be actually done. Okay, so this BCI, which is bulk current injection clamp, okay, they were once commonly used in conductor immunity tests. However, okay, they have largely fallen out of favor, okay, as compared to the other method. So these are some of the key reasons. Okay, so next slide I will explain. These are the key reasons, okay, why these BCI clamps are not widely used in modern conductor immunity tests anymore. Okay, so firstly, okay, the shift actually shift to direct coupling method. Okay, so modern conductor immunity testing standard, okay, actually they emphasize to do this direct coupling, okay, through this coupling decoupling network. Okay, so this direct coupling is actually so-called the keywords of CDN coupling. Okay, so I will explain this again, or current injection through bulk decoupling mechanism like EM clamp. So basically, this is one, okay, the modern conductor immunity. Okay, basically, they prefer to have a direct coupling and they also like to have a form of decoupling mechanism, okay, such as EM clamp, same as for CDN. Okay, so this direct method ensure more consistent and repeatable result by injecting RF signal directly into the cable or system. Okay, because this is so-called coupling. Okay, because of this coupling, okay, this actually ensure more consistent and repeatable result because the RF signal or the noise signal is directly inject into the cable. Another reason is because of the limited frequency range. Okay, so this method PCI, okay, basically they have limitation in the frequency range. Okay, so basically because the frequency range from for this conductor immunity actually there's always an update. So once there's an update, potentially there will be so-called a larger range of frequency that you need to do the testing. And hence nowadays the conductor immunity so-called is often spanned from 150 kilohertz all the way to 80 megahertz, which is considered quite a fair bit of large range of frequency. So this may be some issue to achieve some consistent when you actually do the conductor immunity using this BCI clamp. The use of CDNs and EM clamps actually offer a broader frequency coverage with better impedance control. So basically, in short, okay, because of these two strong reasons, therefore this BCI bulk current injection clamp has been already so-called phased out. So I like to re-emphasize this. So when we actually want to do conductor immunity, we try to use CDN as much as possible. If cannot, then we will fall under this clamp method. Okay, so we will not fall onto this so-called bulk current injection method anymore. So basically, this is actually the second method, which is the EM clamp. Okay, so let me now explain the meaning between coupling and decoupling. Okay, so what's the meaning of coupling? Okay, so this refer to the process of injecting interference signal into the line that is actually connected to the EUT. So for example, if I'm going to power up this EUT through this, let's say this is a power supply. So what they actually do is basically they directly inject the noise into the cable, and this noise actually propagate to disturb your EUT, and basically you just need to observe whether your EUT can still function and all. So basically this is the meaning of coupling. What is decoupling? Okay, so this ensure that the disturbance signal inject into the EUT do not propagate back into the power supply or affect other connected equipment. Essentially, okay, it actually used to isolate the disturbance to the EUT. Okay, so basically imagine this. This is where the noise source here. So basically, once they inject over here, okay, you can imagine that the noise source can actually travel two paths. One is towards the EUT. Another one is basically towards your auxiliary equipment. Okay, for example, this can be a power supply that we actually use to power up our EUT. The noise that we actually inject, they actually can travel two paths. One towards the EUT, another one is basically towards the so-called the power supply. Let's say this is a DC or AC power supply that we go to power up the EUT. So basically with this is what we mean by decoupling. Okay, which means that the noise that we actually inject, okay, we do not allow them to propagate towards the auxiliary equipment. Okay, so therefore, in order to ensure this, we need to have a decoupling. So therefore, when the noise actually inject, they will only move towards your EUT rather than to your auxiliary equipment. So basically, this is the definition of coupling and decoupling. Coupling is basically the process how we actually inject the noise into the cable that is actually connected to the EUT. As for decoupling, okay, so basically the disturbance signal, okay, that we actually inject, that key purpose is to disturb your EUT, and we do not want them to propagate back into the power supply or any other connected equipment. So basically, if you are able to do this, this is what we call the decoupling. So with this, I think it will be easier for you to understand the coupling and decoupling. Okay, so now I like to come so-called a question to test your concept on conductor immunity. Okay, so in the context of EMC, conductor immunity test, the equipment under test may still be considered to pass the test, even it resets, okay, provided specific condition that is outlined by the relevant EMC standard. Okay, for example, IEC 61000-4-6 admit. Okay, so basically, is this correct? So basically, this is what you mean. When I actually do this conductor immunity test, okay, so the EUT, okay, or the equipment that I actually want to test, somehow they actually reset. Can I consider it pass the conductor immunity test, or it consider fail the conductor immunity test? So basically, this is the question. So I ask you whether is this correct. So guys, okay, please just to test your concept. Okay, so try to answer this question through the comment. Okay, so if the answer is yes, okay, so basically please explain why and when then I can consider that it actually passed the test. So if it's a no, then please also share with me the answer whether is it a yes or no. Again, okay, so basically after you have shared your answer through the comment, okay, so once I have gathered enough answer, I will release the solution through the poll. Okay, so basically this is a question to test your concept on conductor immunity. Okay, so similar as listen. Okay, so we know that listen is very key critical so-called component for conductor emission. As for conductor immunity, CDN, basically they are very, very important for us to be able to do this conductor immunity test setup. Okay, so CDN, the key purpose, basically they couple the signal, okay, which is the noise or the RF signal, okay, directly into the cable. Okay, the main coupling and decoupling device parameter, the common mode impedance seen at the EUT, okay, they are actually specified in the table below. So from here, you can see that it may not be so-called consistent 150 ohm. Okay, so you can see that they have this so-called plus minus 20, or plus 60, or minus 45, or plus minus 60 ohms here. So basically, you can see that different frequency, they actually have different common mode impedance. This is because of the L and C. Okay, so later on I will share with you the L and C. Okay, why they have a different common mode impedance. So there are also various form of CDN. So basically, for example, these are the typical AC power supply or DC power supply. So basically with earth connection, etc. So we have this CDN, we have this M1 CDN, M1 CDN, M2, and CDN M3. Okay, so M1, if I don't remember wrongly, is basically for a simple power supply that don't have the earth. Okay, so basically you have the supply and you have the return. So basically this is called the M1. So the M2 is actually for the balance node. Okay, so for differential signal, for example. Okay, for M3 is basically for the three-phase power supply. So therefore, for CDM, we have these three types of CDM. M1, M2, and M3 for different so-called source here. Basically, you can see that CDN, you have also for screen cable, unscreen balance line, and also unscreen unbalanced line, etc. So basically, these are different CDN that can help us to facilitate the testing of conductor immunity, okay, which I will emphasize a little bit more later on. Okay, so next, okay, I'm going to explain what is actually inside the CDN. Okay, so this is actually inside the CDN. Okay, so this box here is actually the CDN. So from here, I like to re-emphasize a few important ports here. So this is where we put our noise. So this is where our power supply. This is where we put our EUT. Okay, so basically you can see that there are a few key important so-called component here. So this is a resistor. Okay, most of the time the resistor is about 100 ohm. There is this so-called this capacitor, a shunt capacitor, a series inductor, and also a shunt capacitor. Okay, so let me explain how can we actually do this testing here. Okay, so this is a proper setup. Okay, so this is the, let's say this is a DC power supply or AC, doesn't matter. So this power supply is to use to power up our EUT. Okay, so this is where we insert our noise source. Okay, so basically the signal generator generate the RS signal, and basically this RS signal become a disturbance. It become a noise source to disturb our EUT. Let me explain this, okay, a little bit clearer. Okay, so from here you can see that basically this EUT, this noise source actually so-called injected inside here. So basically what we want is basically we want it to move towards the EUT. And we also want to ensure that the power supply, it will be able to so-called power up the EUT. So basically we want to have two paths. First path, basically the noise, we want it to be travel towards the EUT. We do not want it to travel back to the power supply. So therefore the noise source, when we actually inject into the CDN, we want it to be moving towards the EUT. As for the power supply, okay, it's the same thing. Okay, we want the power supply to be able to move just towards the EUT. We do not want the power supply to come and kill our signal generator. So the path for the power supply, we do not want it to go this way. So how can we actually stop all this? Okay, so let me further clarify this. Let's take on the next slide here. So these are all the impedance. Okay, so basically this is the impedance for inductor. Okay, you should know that basically is by this equation here, okay, which is the omega L. So basically it's 2 pi FL. So this is the impedance for capacitor 1 over WC, which is 1 equals to W stands for 2 pi F. And basically this will be the impedance for capacitor 1 over 2 pi FC. Same for this. This is actually the capacitor. So let's study the situation, okay, under low frequency. Okay, so the power supply actually supply the signal or the power signal at low frequency. Okay, so typically, let's say about 50 hertz, they actually supply the 50 hertz power supply from the power supply all the way to the EUT. Okay, so what happened here is basically you just imagine that the power supply will come over here. So basically, this is the first so-called obstacle they make. Okay, so basically, this is a very low frequency because it's just 50 hertz. So this is actually 50 hertz. So they multiply by the C, the capacitor. Typically, C is a very, very small number. So therefore, this will be a very, very small number. So when we actually do the impedance, which is 1 over a very small number, this you can imagine that it will become a very, very big so-called impedance because 1 divided by a very small number because the frequency is small. Okay, because just 50 hertz and the C typically is like 10 micro, let's say. Okay, so basically this will make this value become very, very small. And when we actually do 1 divided by a very, very small number, the impedance become a very, very big number. So therefore the power supply, okay, let's say they will not want to move this path. As I mentioned that this impedance will be very, very large and they will not want to move this path. So the current source, imagine that they will continue to move towards the EUT. So once they come into this inductor, okay, let's quickly understand the inductor. As I mentioned here, this frequency is actually a very small number because just a 50 hertz. So from this equation here, you can see that this impedance, okay, will be like a short circuit because this will be very small. Small number multiplied by small number, this whole thing will become very small. And this thing become very small, which is means that they are actually close to 0 ohm, which is a short circuit. So therefore, this impedance will be very small. So hence, the current will continue to propagate towards the EUT. Once they come over here, okay, so the same definition will be the same. Okay, because this is small, 1 over a small number, this will become very big. So therefore, the current will not want to flow this path. And therefore, you can see from here, under the low frequency, the power supply actually will only propagate one path, which is towards the EUT. Okay, so this is how the EUT actually receive the power from the power supply. Now let's take a look on another scenario, okay, which is from the noise source. So over here, I actually inject my noise source here. So once I inject my noise source here, so what will happen here is basically you can see that they will propagate here. So basically the noise source that I inject, they are typically so-called a higher frequency. So once the frequency is considered high, which means that this number, okay, will be a very big number now. or consider quite a substantial big number. 1 over a very big number, this will be equals to almost like 0. Okay, because I mentioned that this is a very big number. So 1 over a very big number, this almost become a 0. So this almost become a short circuit under high frequency. So therefore, the noise source will continue to propagate here because this so-called this capacitor here, they will be like a short circuit. Okay, so once they are over here, okay, then this noise source will disturb your EUT. However, you can see that this noise source will not propagate this path. Why? Okay, remember I told you that frequency is high because the RF source typically they have a higher frequency. So this become high. So basically the impedance become high, and this actually will provide a, a so-called obstacle to prevent the current to flow this path. And because of this, when it's actually a high frequency signal actually inject by the signal generator, they will travel here. The capacitor will be short circuit and they will actually disturb your EUT. The reason why they will not go this path is because the impedance, okay, of the inductor actually will be quite big, and therefore the high frequency signal will not want to travel this path. And this is how I actually receive the power supply at low frequency and my noise source, okay, at high frequency. So therefore, from here you can see that your EUT actually receive two source of so-called one from the power supply, one from the noise source that is actually generated by the signal generator. Okay, so with this, I think you are a little bit more clear, okay, what is actually inside the CDN. Okay, so the impedance of the coupling decoupling device CDN at the EUT port is basically determined by the source impedance at the RF port in series with a 100 ohm internal impedance. Okay, let me explain this. So this resistor typically, as I mentioned, that they are actually 100 ohm. Okay, so you just imagine that typically the resistor inside the CDN is just 100 ohm. So this is what you mean over here. The impedance of the coupling decoupling device at the EUT port is determined by the source impedance at the RF port in series with a 100 internal impedance. So over here, this is actually 100. Okay, so what is say that over here, as long as we have 50, so 50 and 100, they are in series, so therefore they actually achieve this 150 ohm at the EUT port, which means that at the EUT port, we actually achieve a 150 ohm here. Okay, so therefore, we need to ensure that this source here must be equals to 50 ohm. Okay, however, the output impedance of a RF wideband power amplifier, typically they actually deviate from 50 ohm. Okay, which means that the power amplifier, okay, they can't be always at 50 ohm. Okay, so basically they will deviate. Okay, in fact, they will deviate according to the frequency. However, when we actually add a 6 dB antennator, okay, so basically you see that I think it makes no sense that we actually have a power amplifier and then we have an antennator to remove away some of the power. So because of this, okay, these two things actually add up will ensure that we have a 50 ohm. So therefore, then we actually want to put this antennator over here. Okay, so this is what I mean here. Okay, so basically adding a 6 dB antennator to the RF power amplifier output, actually this bring the impedance much closer to the required 50 ohm. So basically from here you can see that this actually become quite near to 50 ohm. So 50 ohm in series with 100 ohm. So therefore we actually have this 150 ohm at the EUT port. Okay, so basically this is why we need to achieve as close of 150 ohm as much as possible. Okay, but like I mentioned earlier on, you can see that basically earlier on I mentioned that they have different common mode impedance, as you can see from here, because of the L and C, which I didn't want to discuss so much, but I think you have some idea because at different frequency they actually have different impedance, and therefore because of this you actually has the so-called some variable, okay, some varies on the common mode impedance. Okay, so let me continue the discussion over here. Okay, so there are actually mainly three form of test level, but you also have this test level X. So test level 1, which is 1 volt. Okay, so basically this is actually 80% AM modulated. Okay, so what you need to do is 1.8 multiplied by 1, okay, which means that it's actually 1.8 if you do this AM modulation here. So basically you can see from here there are actually three test level. The another last test level is actually X. So this is actually a very special okay, so-called which is unspecified. Basically, for example, you have some buffer. Okay, for example, let's say I want to test this test under, let's say I'm doing 10 volt. Okay, I may not want just to test on 10 volt. Maybe just say that maybe I like to do a little bit higher so that I 100% that my EUT can pass the test. Let's say I do like 18 volt, uh, 18 volt RMS value. So basically, these are several considerations that you can actually so-called unspecified the test range that you actually want to do for the conductor immunity. Okay, so basically this is a very simple diagram to so-called showcase how we actually can conduct the conductor immunity test. Okay, so next, okay, so this is also part of the discussion. I'm going to discuss the procedure to do this conductor immunity. Testing conductor immunity involves evaluating the ability of an electronics device or system to resist disturbance induced via its power or signal line. Okay, so this test is often performed to compliant with standard. Okay, for example, this IEC 61000-4-6. Okay, so below is a general procedure for conducting a conductor immunity test. So basically, in short here, basically we inject the noise source, okay, into the cable, okay, that it actually provide, for example, the power supply or whatever comms lines that actually the EUT has. And basically, we inject the noise. We want to ensure that it still function properly. So basically, these are the test procedure when we actually do this conductor immunity. So first step is we need to do some form of preparation. Okay, so we need to know the test standard. As I mentioned earlier on, there are actually three main level to test your DUT. Okay, so firstly, you need to familiarize yourself with the relevant standard, okay, which is this standard IEC 61000-4-6. Okay, so from the standard with different product, you actually will be able to know, okay, what is the required immunity level to test. So basically, this is the step 101. Step number 2 is to do the test setup. Okay, so we need to ensure that the equipment under test is actually under this operation, and basically they need to be configured in its typical operating stage, which means that it must be operate in a so-called normal condition rather at so-called some of the extreme condition here. So basically, we want to ensure that your DUT, they actually operate in a normal condition. So next, we need to identify the ports to be tested. Okay, for example, we need to test at the power. For example, we need to test at the signal, okay, the signaling line, or we also can do the testing under this control line. So basically, this is under preparation. Okay, so preparation, another thing is basically we need to have all the equipment. Okay, so signal generator generate the noise. RF amplifier actually boosts up the RF signal to a large number that can become a noise source to disturb your DUT. Okay, coupling, decoupling CDN. Okay, so which I think is the key topics here. So basically from here you can see that how this CDN actually couple the noise source and also the power source all the way to your DUT. Okay, we also have the current probe. Okay, so basically the current probe can measure the current and also this power meter to measure. Okay, so basically this power meter or they actually can provide a means to feedback to the signal generator, or the spectrum analyzer actually can be a means to feedback to the signal generator whether they want to increase or decrease the level. Okay, so we also have the ground plane and some of the insulating supporting table. Okay, so the table typically you need to have an insulator table, and we have this ground plane. Basically, let me just show over here. You can see that when you actually do the testing on the UT, you actually want to put in an insulating support, okay, which is about 100 mm here. So basically, this is what it means over here. Okay, so about the test environment, okay, although it's not necessary, but we actually prefer to do this testing in a controlled environment. Okay, for example, in a show room. Okay, so as to minimize the interference. For example, the noise can actually become a so-called they couple into the path. Okay, which means that they couple into the cable, and this can become an issue. And because of this, we actually prefer to do in a showroom. We minimize the interference as much as possible. Okay, next, okay, under calibration. Okay, before we test the UT, we need to set up the calibration loop. Okay, so I mentioned earlier on, firstly, the noise will be generated by the signal generator. CDN will ensure that the noise that you actually generate from the signal generator will be able to reach to the EUT. We also need to measure the power. Okay, let's say the power is not enough, then this power measurement actually will create a feedback to the signal generator. Let's say now it's not enough, So therefore, the signal generator will increase the so-called the transmission power. So more power will be reaching the CDN, and then again from here, more power will be able to reach the EUT. So basically, this actually provide a form of feedback to the signal generator. Okay, so as a form of indicator whether is it enough power or not enough. Adjust the signal level. Okay, so basically you generate the RF signal. So this is the frequency range that typically as we follow the IEC standard. And what we need to do is basically we need to adjust the output of the signal, okay, the amplifier, so as to achieve the required voltage at the CDN output. Okay, so earlier on I mentioned that there are actually three main types. Okay, 1 volt, 3 volt, and 10 volt. So basically we need to ensure that the so-called the voltage that you create the noise source, they must be consistent, and this is basically what it means here. So basically, we need to have some form how we can actually adjust the signal level. So next, we need to record the reference level. Okay, we need to verify and record the test level across the frequency range. Okay, next will be on the testing. So basically, we connect the DUT, okay, to the CDN. Make sure you connect to the right port, okay, because as you can see that they actually have also possible to the auxiliary port. So make sure that you connect your EUT, okay, at the so-called indicate. Okay, most of the time the CDN actually will indicate that this part is actually connected to the EUT. So make sure you connect to the correct port. Okay, so you need to ensure proper grounding between the EUT and the test setup. Okay, so next is on the injection of the disturbance signal here. So as I mentioned earlier on, the signal generator actually so-called generate the noise source. Basically, they will inject the RF signal into the DUT cable, okay, via the CDN. Okay, so basically they will switch across the frequency range. Okay, so basically from 150 kilohertz to 80 megahertz. Okay, while they want to maintain the test level as much as possible. So keep this in mind, the test level cannot be consistent, okay, which means that 3 volt all the way or 10 volt all the way. So there will be some variation, okay, while they will try their very best to maintain the defined test level as much as possible. So next, we just need to monitor the EUT behavior. Okay, we want to observe whether the EUT have any malfunction, degradation of performance, or some failure to operate as in intent. Okay, so we need to know any deviation from the accepted performance criteria. Okay, so next, okay, so basically the criteria when we actually do the evaluation, okay, we use predefined performance criteria, for example, class A, B, or C. Okay, so basically class A, which means that there is no degradation of performance, which means that everything worked fine, nothing happened. Class B, actually there it will be some form of temporary loss of function, okay, which is self-recover, which means that they will automatically reset and recover by itself. You don't need to do anything to make the EUT actually recover. So because of this, there is actually some temporary loss of function, okay, but it will be a self-recovery. Next will be on the class C, which means that again the loss of function. Okay, however, you need to require to do some intervention, then you can recover the fault. So basically, under this class C, okay, most of the time you actually don't pass the conducted immunity test. Class A, class B, okay, class A sure pass. Class B, I will say that maybe can pass, maybe cannot pass. Okay, so next on the documentation. Okay, so the test result actually document all the EUT behavior at all frequency point and also at all test level. Okay, as for test level, this is my experience. Okay, let's always start from the low one. Let's say we start from 1 volt. Okay, let's say your DUT actually required to test at 10 volt. So basically start from the very low one, 1 volt. Okay, if your DUT cannot survive 1 volt, then there's no way to straight away stress them at 10 volt. The 10 volt may kill them. Okay, so therefore you would like to start at a very low level, which is 1 volt, and you see your UT can function okay or not. Then you can go for 3 volt, and then finally you can go for 10 volt. Okay, observation, okay, document any failure, deviation of anything that you actually, for example, the signal actually deviate or any observant during the test. Okay, for the test report, okay, compile a detailed report, okay, which include the test condition. Okay, you also need to indicate the temperature and humidity, the equipment that you use, copy down all the model and also serial number, the whether the equipment calibrate or not. So basically, you can, for example, indicate the calibration date, etc., and the EUT configuration and performance criteria. Okay, so with this, okay, I like to end my discussion. In this video here, I have discussed what is actually inside the CDN and what are the test procedure when we actually do this conducted immunity. Okay, so guys, again, if this video helped you, please sharp to like and share with your friend. And also, if you learn something from this video, please consider to subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.